Alright, well this is a video for Probability Day 7, Unit 14. Like usual, I want to start with a warm-up. So this is kind of a practice of yesterday's stuff, and we did the multiplication rule. It says the table shows the results of a survey in which workers between the ages of 26 and 45 were asked if they have at least 1 month's income set aside for emergencies. So you can see it's broken down by men and women, either have less than 1 month's income or 1 month's income or more. It says if 2 different workers are randomly selected, find the probability that they both have 1 month's income or more set aside for emergencies. Round your answer to the nearest percent. Alright, well, based off of what we did yesterday, take a couple minutes to see if you can figure out what your answer would be to this. And maybe hit pause on the video while you do that. And when you're ready to see the work, hit play and see if you got it right. Okay, let's see how you did. So what we're really looking for is the probability that they both have more than 1 month set aside for emergencies. So I'm just going to say probability that they have income and they have income. So it's an and because you want the first person to have it and the second person to do it. Since it's 2 different workers, that means it's without replacement. So the probability is going to change. It's not an independent probability. So what I need to see, it doesn't really matter if they're men or women, that doesn't really come into play. So you might want to total these up. So if I do 66 plus 83, so 66 plus 83, that comes out to be 149. So this total over here is 149. And if I do 76 plus 62, that total is 138. I'd always recommend in these two-way tables just always getting all the totals down, whether you need them or not. 66 plus 76, that's 142 again. And then if I, oops, that goes there. And if I do 83 plus 62, it's 145. And the total of all of them, I do 145 plus 142. We get that there are 287 people total. Okay, so we want the probability that they both have 1 or more months income. Okay, so the probability that the first person that you choose, if you just randomly select, has 1 month's income or more, is 138 of those out of the 287. So it'd be 138 out of 287. And since it's and, we multiply. Since it's without replacement, so that person's been chosen, we have to choose another one now. So now there's only 137 of them left out of 286. So when I multiply those probabilities, we have 138 out of 287 times 137 out of 286. Gives us that decimal, which we will put to, oh, it doesn't round, so it's 0.23 blah blah blah, but I said to the nearest percent, so let me check again, 0.230. Okay, so that's about a 23% chance. Okay, so even though this question didn't specifically say and in it, you had to kind of infer that it would mean this person has it and this person has it. Okay. So today, if you switch over to the note packet, hopefully you have a copy of the notes. If you don't, you can print it off my website. But today's kind of a practice day, putting everything together. I know it's kind of tricky trying to know what to do when with all these different probability rules. So first, I thought we would start with just filling out this review of probability rules on the front here. Okay, so let's look at the different scenarios. Given event A and event B, so we've got 2 different events. The probability that event A or event B happens. Now, or means add. So if you're thinking in terms of union and intersection, this is probability of A union B. And in terms of the Venn diagrams, or means I want anything that's in either circles A or circle B. But you got to be careful of that counting twice in there. So if A and B are mutually exclusive, remember, what does that word mutually exclusive mean? Remember, that means no overlap. If they're mutually exclusive, so if A and B have absolutely nothing in common, then you can just add the two probabilities together and not worry about it. So it would be saying that the probability of A union B is the probability of A plus the probability of B. If they're not mutually exclusive, that means I do have overlap. And that means if I've got circle A over here and circle B over here, that there must be some section in the middle where they cross. In that case, you don't want to double count, because remember, if this is probability of A plus this is probability of B, I just counted this middle section twice. And I can't count that middle section twice. So to deal with it, we would say that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of that overlap, which is A intersection B, or A and B. So don't forget to subtract the overlap if they're not mutually exclusive. Okay, so that's if it says or if the problem infers or. Next one is if it says the probability that event A and event B occurs. And means multiply. And now I'm looking for the probability of A intersection B. Okay, so if A and B are independent, if one has no effect on the other, then it's easy. Then we just multiply them. Probability of A intersection B equals the probability of A plus the probability of B. And by plus, I of course mean times. Sorry. Probability of A times the probability of B. If A and B are not independent, then you kind of have to worry about the conditional. So that means probability of A intersection B is equal to the probability of A times the probability of B, given that A's already happened. Or you can do it the other way also, probability of B times the probability of A, given that you know B's already happened. And that's only when you have to worry about them if they're not independent. This is like in the warm-up when it said without replacement. That means they're not independent if you're not replacing it, because what you pick first has an effect on the probability of what you pick second. So sometimes this is just as simple as like the warm-up where we decreased the numerator and denominator by 1. That was essentially taking the probability of the second person having more than a month's income, given that we knew the first person already was chosen with enough income. Okay, so that's that. So and versus or. Earlier in the unit we did conditional probability. Probability that A occurs given that you know B already happened. So that'd be the probability of A given B, and that's a formula. It's the probability of A and B occurring divided by the probability of B occurring. So it kind of takes out the probability of B happening because you already know that it does. So similarly, the probability that B occurs given that A occurs, probability of B given A would be the probability that they both occur, B and A, but divide out the probability of A. We don't want to consider that because we're given that that already occurred, so that doesn't need to factor into our chance. Okay, and then finally some tests for independence. Sometimes we have to figure out if two scenarios are independent. So remember, independent just means A and B, the two cases I'm looking at, have no effect on each other. And sometimes it's obvious, like if I draw a card and flip a coin, whatever card I draw is not going to affect what the coin flip is. But in other scenarios, like the probability of it raining, given that it's cloudy out, well, if it's cloudy, there's a higher chance of rain than if there's not cloudy. So there's two tests for independence. So you can kind of do it by definition. if you can prove that the probability of A given B is the same as the probability of A alone, or similarly, the probability of B given A is the probability of B alone, that means they're independent, because that means knowing that event B occurred had absolutely no effect on the probability of A occurring. That's literally what this is saying, which is what independence is defined as. And then there's also this thing called the product test for independence, which we saw a little bit the last couple days. And that goes back to an earlier rule that we did. A and B are independent if and only if, that's what the IFF stands for, probability of A intersection B is equal to the probability of A times the probability of B. So if you can prove that the probability of two things occurring together are the same as multiplying them separately, then that means it's independent also. And that kind of goes along with this rule. If A and B are independent, we can say that. So that's another test for independence. They kind of work hand in hand. Okay, so now that's kind of everything all in one spot. The examples on the next 2 pages are going to take you through different scenarios. You're going to have to figure out what to do when. And these are Regents level questions. So let's go on to the next page. Here we go. Okay, example 1. A survey of registered voters in a city in New York was carried out to assess support for a new school tax. 51% of the respondents supported the school tax. Of those with school-aged children, 56% supported the school tax, while only 45% of those who did not have school-aged children supported the school tax. If a person who responded to this survey is selected at random, what is the probability that the person selected supports the school tax? Okay, well, there's lots of words here. Sometimes it helps to kind of write everything out in probability notation. So let's go through this again. We've got a survey of registered voters, blah, blah, blah. 51% of the respondents supported the school tax. So let's call that S. Oops, that looks terrible. Let's try that again. We'll call this event S up here. Well, it doesn't want to work there. So we'll say S is supporting the school tax. So we know right now that the probability of S amongst all the registered voters is 0.51, 51%. Of those with school-aged children, 56% supported the school tax. So you got to read through the lines here. That's saying, given that they have school-aged children, 56% supported the school tax. This is a known, school-aged children, so that's given. Let's call that C for children. So the probability that they support the school tax, given that they have children, is 0.56. While only 45% of those who did not have school-aged children supported the school tax. So this is still probability of support given not children. So I'm calling that children complement. Remember, complement means not. That's 0.45. Okay, so now let's see what they're actually asking for. The probability that the person selected supports the school tax. Well, that's given to us right there. That's 0.51, 51%. So just writing out those words gave us that answer. What's the probability that a person supports the school tax given that he or she does not have school-aged children? So that's literally the probability of supporting given they do not, so C complement, have children. Again, given to us right in the words, 0.45. Okay. Are the two events has school-aged children and support school tax independent? Explain how you know this. Remember, there's 2 tests for independence. Since I've got givens here, then probably it'd be best to use the givens. So remember, for a test for independence, probability of A, if it's independent, probability of something happen given that B occurs would be the same as just the probability of that something happening. B occurring had no effect on A. Well, look what we have. I know that the probability of supporting the tax, given that they have school-age children, if I'm checking, is that equal to the probability of just supporting? So in other words, did having children have no effect on that probability? And the answer is no. Probability of supporting was 0.51. Supporting, given that they had children, was 0.56. So 0.51 is not equal to 0.56. So what's that tell us? Not independent. So it says explain. I would say not independent, meaning they are dependent, since probability of S given C is not equal to probability of S. The fact that they had children changed the probability that they supported the tax. And I'm just looking back at what I wrote over here. It looks like I wrote these backwards. Sorry about that. So this really should have been 0.56 is not equal to 0.51, which makes sense. If they had school-age children, a little bit more support for the school tax. Okay. Part C, suppose that 35% of those responding to the survey were over the age of 65, and that 10% of those responding to the survey were both over the age of 65 and supported the school tax. What is the probability that a randomly selected person who responded to the survey supported the school tax, given that he or she was over the age of 65? Again, you really need to write this in probability terms. Let's call this greater than 65. So we know that the probability that someone greater than 65 responded to the survey was 0.35. It's a nuke event. 10% of those responding to the survey were both over the age of 65 and supported the school tax. So that means probability over 65 and support was 0.10. We want the probability that a randomly selected person who responded to the survey supported the school tax, probability of support, given that they were over 65. So now I'm using the conditional probability. And remember, the first thing I would turn to is the formula. This would be probability support and over 65 divided by probability of support. And let's see if we know that. Support and 65, well, it's the same as above 65 in support. So that's 0.10. I think probability of support we knew from before. That's 0.51. So then if I use my calculator here and say 0.10 divided by 0.51, we get 0.196. And I paused because, sorry, not on my game today. I made another mistake here. I know. It's probability of support and greater than 65, given that they were 65. So I should have put the probability of 65 down here. Again, sorry for this confusion. Hope this makes sense. Really what I'm just doing is I'm using the formula. Probability of A given B. Probability of A and B over B. It's B that you got to divide by. That was the mistake I made. So it's over 65 I got to divide by, which is 0.35. So let's try that again. 0.10 divided by 0.35. 0.2857, blah, blah, blah. Didn't say what to round to. Let's see if it math fracts. It does. It's 2/7. If you want to use the percents like they did in the rest of the problem, it'd be about 29%. Okay? So hopefully that made sense, even with the slight bobble there at the end. Let's go on to the next one. In contract negotiations between a local government agency and its workers, it is estimated that there's a 50% chance an agreement will be reached on the salaries of the workers. It is estimated there's a 70% chance that there will be an agreement on insurance benefits. There is a 20% chance that no agreement will be reached on either issue. Find the probability that an agreement will be reached on both issues. Okay, so just like I said last time, let's do probability terms. We've got probability of 50% that it'll be reached on salaries, so let's call that event S. So probability of S is 0.5 or 0.50. 70% chance agreement on insurance, so let's call that I. Probability of I is 0.70. No agreement, so probably there's no agreement means probability not S and not I. Not S and not I is 0.20. We are looking for the probability of S and I. Probably they'll both be reached together. So, and usually means I'm multiplying. But what do I have to check if I'm multiplying? I need to check are S and I independent? I don't know. It doesn't say that they are. It doesn't say that they aren't. Ways to prove independence would be using conditional probabilities, the givens, which I don't have any givens, or using the product rule, but that's what I'm trying to find. So I don't really have a way to test if they're independent, which means I probably shouldn't just multiply these two probabilities together and call it a day. Now, this might not seem obvious at first, but I've got two separate events. Anytime I have two separate events, it's not a terrible idea to make a Venn diagram. So let's call this S, we'll call this I. Now remember, you're supposed to fill in the middle section first. That's what we're looking for. So we can still do it, we'll just call it X for now. So if this is X, what would go in this side of the S circle? Now normally we take the probability and subtract the middle. So I'll have to do that, 0.5 minus X. Same with the I circle. I'm going to take 0.7 minus X. And what goes on the outside? Well, we know that. There's no agreement on either issue. That's 0.20. So it comes down to how do I figure out what S is? What X is, sorry. Well, what do you know about a Venn diagram probability chart? What should everything inside it add up to? Well, there's no other option, so everything should add to 1. So if I do 0.5 minus X plus 0.7 minus X plus 0.2, that should equal probability of 1. Combine like terms, you've got 0.5 plus 0.7 is 1.2 plus 0.2, that's 1.4. These two x's cancel, we've still got a minus x there equals 1. And if I think of adding the x over, subtracting the 1, I get that x is 0.4. Well, that's what I was looking for. I was looking for what goes in this center here. That was x. So that means the probability of salary agreement and insurance benefits is 0.40 or 40%. Okay, so if you know to use the Venn diagram, it's not that hard of a question. But again, the way I knew to use it, I didn't have the right test for independence, so I couldn't just multiply the two probabilities. I didn't have any other information to find probability of S and I, so I went to the possibility of a Venn diagram, given that there were only two events. Okay, part B. Based on your answer to part A, determine whether the agreement on salaries and the agreement on insurance are independent. Justify your answer. Okay, well now I have to figure out independence still. I still don't have any conditional given probabilities, so I should say, is the probability of S and I equal to the probability of S times the probability of I? Because that's the multiplication test for independence. Well, is 0.40, which we just calculated, equal to probability of S, which was 0.50, times probability of I, which was 0.70. And something tells me they're not going to be. 0.50 times 0.70, 0.35. So it's close, but not close enough. So 0.40 is not equal to 0.35. So no, not independent. And it says justify. If the region says justify, math work is sufficient. So the fact that I showed this does justify. I don't have to explain anymore. All right, last one. The results of a poll of 200 students are shown on the table at the right. For this group of students, do these data suggest that gender and preferred music styles are independent of each other? Okay, it's another independence question. And this is a two-way table. I've got females and males and 3 different types of music. We talked about this in the warm-up. What do I suggest you do first when you've got a two-way table? If the totals aren't there, I would suggest totaling them up. So total down this column, this would be 90. This column here would be 65. This column here looks like 45. Total of the rows, 45, 25, and 27 is 106. 36, 40, and 18 are 94 for a total of, no matter which way you add, 200, which is what we were supposed to have. Okay, so it says, all it says are gender and preferred music styles independent. So we need to just pick any one of the music styles. Doesn't matter which one. Which one do you want to choose? Techno, is that what you said? Okay, we'll do techno. So I want to check, does the probability female given techno equal the probability of female? So in other words, does techno have no effect on the probability of being a female? Let's see. Probability of female given techno. So given techno means I'm only looking at these 90 people. And the probability that you're female in those 90 people are 54 out of 90. So 54 out of 90, is that equal to just the probability of being female? You need to look all the way across the female row. There's 106 of them out of 200. Are those two fractions equivalent? Well, it doesn't look like it to me, but let's check. 54 out of 90 is 0.6. And 106 out of 200. .53. Not equal. So therefore, not independent. And all they said were gender and independent of preferred music styles. It didn't specify which one I had to use, so you could have done the same exact thing with female given rap, female given country, male given techno, male given rap, male given country, and gotten them. None of them would be independent either. All right, well, hopefully that's a review of independence and some of the other probability rules that we've done. Hopefully you have a homework sheet. If not, you can print it off my website. And good luck with everything.